A warm and graceful afternoon to one and all present in the meeting, and a very good morning to our invited guest, Dr. Imad Faruque. First of all, I would like to thank our Pro-Vice Chancellor, Engineering and Technology, Dean, College of Engineering and Technology, HOD, EC Department, all the faculty members of EC Department, and the management for giving us the opportunity to host this event. It's my privilege to welcome you all to this event. A very special mention to our invited guest, Dr. Imad Faruque, for gracing us with your presence. Also, I welcome all the participants who have joined us virtually for this workshop. The Department of ECE, SRMIST, in association with the Optical Society of America and the Optical Society of India, is organizing this virtual workshop on photonics and photovoltaic devices. WOPPD is conducted biennially and this is the fourth edition. The aim of this workshop is to provide a clear pathway to access the photonic technologies available to researchers in India so that more of our big ideas can be transformed into solutions. This workshop will provide an introductory overview of various topics like ML in photonics, visible light communication, and teleportations on a photochip. Yesterday, on the day one of WOPPD, we had Dr. Daniel Melati, who threw light on the machine learning techniques for photonics and also grating couplings and metamaterials. Now, I call upon Mrs. Diana Emerald Asha, Assistant Professor at Department of ECE, to introduce our speaker, Dr. Imad Faruque, to the participants.
Good afternoon all. With immense pleasure, I wish to welcome the chief guest of today's session, Dr. Imad Faruque from the University of Bristol, UK. I deem it a great privilege to brief you about his credentials in academics, research and extension activities in photonic science and engineering. The resource person, Dr. Imad Faruque, graduated from our neighboring country, Bangladesh, in electrical and electronics engineering. It is quite surprising that an undergraduate from the East was fortunate to get Erasmus Mundus scholarship for MSc study in photonic study and engineering in University of Bristol and University of St. Andrews in Europe. While pursuing his research in photon-pair generation in photonic crystal fiber, in post-graduation, he had traveled widely in order to broaden his outlook in research and outreach. Dr. Imad was gifted to have been selected for Marie Curie PhD position in QET lab on silicon quantum physics under the guidance of Professor Mark Thompson and Professor John Rarity. During his doctoral research work, this resource person has investigated photon pair generation for quantum technologies. On behalf of the faculty of ECE and OSA student chapter, I welcome you once again to this virtual workshop organized by the SRM OSA student chapter. I have the hope that your deliberation in today's workshop will immensely broaden our scope for further research and development in teleportation in photonic chip. Thank you, sir.
Thank you, Professor Diana, for this kind introduction. Shall I share my screen for the presentation?
Yes.
Yes.
Okay. Oh, I cannot share this screen. Maybe.
Ma'am, you have
enabled.
to.
I have given.
Okay. Can you share my screen?
Yeah.
Can I see my screen?
Yes.
Yeah. Okay. All right. So I'm Imad Faruque. I'm a research associate in KET Labs in Bristol. Before I start my talk, I actually want to thank all the organizers in the SRM Institute of Science and Technology for arranging this workshop, particularly the OSA chapter and the OSA traveling lecturer program for this to have this opportunity to present my talk in a virtual environment, though. But like I think it's really amazing, like how broad the scope is of these programs to go very different places and like very far away. But it is really nice. I'm glad. Particularly, I want to thank Dr. Hankati and Professor Shanti Prince for inviting me to this workshop to deliver the lecture. So I have been part of OSA for quite some time, and although I'll be basically talking about research in this talk, but you're more than welcome to ask me other questions about my experience in the OSA. So I have been a treasurer for 2 years when I was PhD student of the OSA student chapter, and I also did a lot of outreach and public engagement. So any questions is welcome. So with that, let me start with teleportation on a photonic chip. Okay, so let me also change the pointer option to this pointer pen. Okay, yes, that's nice. All right, so let me start with the motivation. And this graph actually sums up most of the motivations of the quantum technology. So this has been taken from Google's research direction for quantum technology or quantum computing. So what it shows here in this graph is that the state where we are at the moment with quantum technology. So we are actually here on this part, and this part where we actually try to build quantum systems, or we have built actually quantum systems, which can be verified with classical computers. The error rate is quite high, and the number of quantum bits, the qubits, actually above the order of 10. So what we want to do actually, we want to go towards something with 100 qubits in the near term, maybe in the next 5 years. And eventually, maybe in the next 10 years or so, we want to go 1 million qubits. So although this is a very specific platform from Google, but this graph actually is true for most of the quantum technology platforms. And that includes the superconducting qubits, which are the main area of implementation of quantum technology for Google, IBM, or these big companies. But there have been also a lot of other platforms, and none of them actually has been proven to be the best platform yet. So the competing platforms includes ion traps qubits, like ion traps quantum computing or quantum technology. And then there are solid state spin qubits as well. And then also there are photonic qubits. So we basically work with in GET Labs with photonic qubits, and there are also some solid state spin qubits as well. So the main idea, because we want to reach to a goal where we can actually have 1 million qubits. So that's why we need optical technology, which is scalable and complex, like it can implement complex algorithms, and it can scale up from 10 qubits to 1 million qubits. So that's quite a big task. Since our approach is with photonic qubits, I'll briefly mention what these things are, the backgrounds of the photonics. So I don't know actually how many people are familiar with photonic circuits or photonic chips. Nevertheless, I will just give a brief background so that we are all on the same page. So the idea of photonic circuit is that we have something like electronics, but rather than electrons, there'll be photons in a circuit. So to give an example, in electronic circuits, say for example, the processors or the architecture of a processor, what we have in electronics, we have an input, we have an output, and then we have a processing in between that that transforms the input to the output the way we want. I mean, this is how our mobile phones or the laptops or any computers, that's how it works. And we have actually the electronic gates, the AND gates, the OR gates, all these combination logic gates that actually helps us processing or helps us implementing a certain algorithm in electronics. In photonics, the inputs, outputs are basically like through the waveguides, and instead of the electronic wires that connects all these different components in electronics, we have waveguides, optical waveguides. And then the processing has a lot of different types of components. It's not like simple AND or OR gates, but it has a lot of things which can manipulate the photon. So I want to actually explain a little bit the different types of photonic components before I go into details. So say for photonic components, the input outputs actually are made of or consist of lasers, fibers, waveguides, and different type of couplers to couple light from outside into the chip, photonic chip, and then detectors to detect the photons. So it's slightly different than electronics in the sense that in electronics, we just have like we put electronic signals so easily on a chip, electronics chip, we don't actually have to think about where the electronic signal is coming from. But for photonics, we actually usually have a laser which actually produces the photonic state or the optical state, and then we have some sort of fiber, and then we have some sort of creating structure here. Sometimes we also have edge couple waveguide, and that fiber and this kind of structure actually couples the light from outside from the laser into a photonic chip. And then after the light is coupled with the chip, there are different types of waveguide depending on the application, whether it's strip waveguides, rib waveguides, slot waveguides, or photonic crystal waveguides, which then carry the light around the chip. The waveguide usually acts as a electronic wire. This acts as a very similar to electronic wire for electronic chip, in the sense that it actually carries the photon around the chip and send it to the components that needs to be that does the manipulation or the processing of these photonic states. There are more input-output structures or components and other things that I'm not really going to explain much, because I think that will that will make me diverge from the actual talk. So for manipulating the photonic states or the optical states, there are quite a few components. Among them, I want to specifically mention a few of them that will be useful to explain the teleportation photonic chip. So on the left, actually, here there is a beam splitter. Beam splitter usually in optics means that we split the light intensity. Here is basically showing the idea of the beam splitter, but not on a photonic chip. So here, say the idea of implementing a beam splitter, one of the ideas is actually wave tunneling. So that's why I actually put this figure on the left. So in this figure, what it's showing is that when we have the total internal reflection on a prism, for example, say, and the light just completely bounces off from the boundary of the prism and the air. And then if we bring another prism very close to it, then there will be wave tunneling. And by controlling the gap between these two prisms, we can actually control how much light would be traveling from one prism to another or within the same prism. So this is exactly the same idea when we try to split light on a photonic chip. So we bring two waveguides very close together, and the waveguides, the light travels inside the waveguide is usually explained through total internal reflection on the boundary of the waveguides. And when we bring these two waveguides very close to each other, then the same thing happens, and then we can control basically the splitting of the photonic state from one to another. So this is the direction. This is called basically directional coupling in photonic chips. And this whole process of this splitting of the wave tunneling in this sense is called frustrated total internal reflection. So to manipulate the photonic state, the other very important component we need is the Mach-Zehnder interferometers. And the interference is the key effect actually manipulating the photonic states on chip. So Mach-Zehnder interferometer, when it's symmetric, it is quite versatile. It can be used as a switch. For example, if I input light from the top waveguide, I can basically manipulate the phase here, or I can control the phase here, so the light comes out of the top waveguide or the bottom waveguide, or I can make it the phase such a way that the light is placed half, like 50% in both waveguides. And actually, if I make the path length of the two arms of the Mach-Zehnder interferometer different, then it becomes the asymmetric Mach-Zehnder interferometer, which actually has a response in terms of wavelength, and thus it can also act as a filter. For example, if we vary the wavelength on the bottom axis and we plot the output from one of the output waveguides, then we can see there is a sinusoidal or cosinusoidal response from this splitting, which the transfer function of these Maxent interferometers can be basically written as in a transfer matrix in this way, which is basically showing the response is sinusoidal or cosinusoidal. Although actually, I think probably I should have mentioned that how it looks like a Maxent interferometer, just to make a comparison or an analogy with like non-chip, like bulk optical components. So the reason it's Maxent interferometer because there is a beam splitter here at the beginning, which splits the light into two paths, and then it travels through these two paths and has this phase, this phase in one of the paths that we can control, and then it's being combined again. So that is basically the definition of Maxent interferometer. So this kind of structure, when you look at the photonic chip, it basically says that there is interference going on. So I think this is a bit different perhaps with bulk optics, where in bulk optics, Maxent interferometer can have many different geometries. With photonic chip, there can be many geometries, but this is the most common one. And this is what we're going to see in future slides. Okay, let me go to the next slide. Here I actually want to ask one very interesting question. I don't know how many of you actually know about it, but maybe I think if you don't work with quantum photonics, then maybe you have not come across to it. Actually, I haven't come across to it before I started doing quantum photonics. So this is a very simple question. The question is that, let me go back to the last slide. So we see there are interference going on here, and the transfer function of the interference is showing sinusoidal output from one of the waveguides of the optical state. Say the intensity is coming from the left, and the intensity we see on the right, it will have a sinusoidal fashion as a function of the phase. So we assume that the interference going on here is sinusoidal because this is the way we have these equations, the superposition equations, when we do this calculation for the Mach center. But if I ask, then how actually it works in single photon level. So what do I mean by that? So what I mean is that a light consists of photons, right? Any optical light intensity. If we actually go deeper, for example, if I say a matter consists of atoms, right? So the constituent of matter is atom or molecules. Then if I talk about light, then if I have an optical state, then if I try to see really deep inside what it's made of, then it's all made of single photons. Then how does interference occur in single photon level? So that's actually a very interesting question, and the result is actually very surprising. So this was first observed by Hong, Wu, and Mandel in 1987. So it's not very long ago that they have seen it. So let's see if I can explain it. So say consider we have two photons. So a light is made of a lot of photons. So we are just taking the whole event at a single photon level. So we are going to see when in beam splitters and beam splitter, two light photon, like the photons, like the smallest part is incident, then what happens? So there can be actually two possibilities. So let me break down. If there is only one photon, the photon can either transmit through the beam splitter or it can reflect through the beam splitter. And by the way, let's consider that the beam splitter is 50-50. So then it has equal probability of reflecting or transmitting. Now, there are four possibilities for two photons then. So the first possibility is both photons transmit. Then the second possibility is both photons reflect. And the third possibility is the one photon reflects and the other photon transmits. And the fourth possibility is actually the same. The first photon is transmitting and the second photon is reflecting. So it turns out that if the photons are completely indistinguishable, like they are the same in all degrees of freedom, polarization, color, and spectral shape and everything, then the photons will bunch together always. So they will never reflect, or both of them reflect, or both of them transmit. So the only possibility, if the photons are completely identical, then they will both transmit or both, they will bunch together in either of the ports. So this is actually a very important phenomenon, and this is actually one of the basic or the fundamental building block of quantum technology for photonics. So we may come across to it in a later slide, but let me move forward. So so there are a lot of photonic platforms actually inside the photonic qubit. There are also a lot of photonic platforms. So the one we are interested in is silicon photonics. So why we're interested in silicon photonics? So among all the components, the photonic components on a chip we have, the silicon photonics is the most mature one. And it also have actually shown the electronics and photonic integration. And it has a lot of high-speed components as a switch, which is very important when we scale up. And it has low loss delay lines and other good components as well. But the main reason I suppose people actually are interested in silicon photonics is because the silicon electronics industry is the one which actually revolutionized the way we work with computers. So the silicon electronics at the moment, I think my data might be outdated, so it has been taken a few years ago. So say the best processor at the moment we have has about billion transistor, and we have a lot of computing power in our laptops and phones, and that has been possible mainly because of silicon electronics industry. So since our goal is to go to 1 million qubits, and we have electronics industry, silicon electronics industry, which already can pack about 1 billion transistor. So we can hope that silicon photonics can go the same way and have that sort of electronic packing density and as well. So we can get about 1 million qubits with a photonic chip. So let me actually break it down a bit, how we're going to implement in silicon photonics such a 1 million qubit technology. So photonic qubits are basically made of single photons, and the basic building block of information that we use for quantum photon technologies are called quantum bits. So quantum bits are superpositions of classical 1 and 0. So here I'm showing a specific implementation of a qubit on a photonic chip. So it's called dual rail qubits. So it's a path qubit. So what it means is that in classically, say if the photon is on the first waveguide, then we get a signal of 1. And say if the photon or the optical signal is on the bottom waveguide, we get sorry, I swapped this to 0 and 1. So say if in the top waveguide, then we call it 0, the signal, and if the photon is at the bottom waveguide, we call it 1. So in E qubit, what we say is the photon has the probability of being in the top or the bottom waveguide, and thus we actually have a superposition of 0 and 1. So there are two very important things here. First is that when we measure a qubit, we find the photon either in the top waveguide or in the bottom waveguide. We should never find it in both of the waveguides. So if there are photons in both of the waveguides, then there are more than one photon, and then that's an invalid qubit. So that's one of the very important thing here. So a qubit is a superposition of 0 and 1, and it actually shows the probability of being in 0 and 1, and that's how it contains a lot of information. But once we measure it, it only takes one of the states, not all these different states from the superposition. And it is normalized. So alpha square plus beta square will be equal to 1. Now I actually want to ask something to the viewers. I mean, I'm not really looking for the right answer. I'm just looking for introduction. So if I ask the viewers, then what would be the main difference between a classical information 1 and 0 and a qubit So in reality, when we deal with these photonic qubits or any qubits, so what would be the main difference or fundamental difference we will see? Does anyone want to respond? No one? Can people hear me?
Yeah, we can hear you, Dr. Imad.
Yeah, right. Yeah, so I mean, any answer is valid. Like, yeah, I mean, you can say anything. Like, what do you think? Like, what would be the main difference between a photonic qubit and just a classical bit?
There'll be uncertainty.
Yeah.
Unlike in classical, when you move on to quantum, you can expect an uncertainty.
Right.
That's the main.
Yes, there could be uncertainty if we don't know the state of the qubit. Okay. Yeah. Anything else? Anyone else want to say anything? Okay, let me ask the question then. By the way, I mean, you can stop me anytime, and if you don't understand anything or if you want to ask anything that I'm explaining, you can ask me. You can stop me anytime. So, yes. So the fundamental thing that actually I would say I find it very different from quantum bit to classical bits is the way we copy or send information. So for classical bits, we just say we copy something. Like in our computers, we are copying 100 times a day, or we are copying it to external hard drives or USB sticks, or if we just send to cloud sometimes. So copying is like very common in classical information, and we don't even think about it second time when we copy something. But let me explain how copying is so different for when we talk about qubits. That's mainly because of superposition though, but let me explain a bit more detail. So say, let me actually change the pointer. So say, for example, we define the action of copying with the unitary transformation. So this U basically is defining a transformation. So U is basically a transformation. Then say we define the act of copying classically in this way. Say we have a state 1, the classical bit 1, and we have this empty space in B. And we want to copy this 1 from system A to this empty space in system B. And this unitary transformation is actually the action, the physical action that copies 1 from A to the empty space in B. So then the outcome of this transformation is basically both A and B has this 1 in that particular position. So the same way we can copy 0 for classically. Now, say in quantum mechanically, we want to do the same. So what we have is the quantum state, which is psi, which is a qubit, for example, and then we want to copy it to this empty space in B. So then after transformation, we have both the qubits in system A and B. But the qubit is a superposition of 0 and 1, right? So what happens here is that if I just plug back the equation of superposition of qubit, then I have this left-hand side, and the right-hand side, what we need to have is this state. So we copy both the qubits in both system A and B. We have the qubit both system A and B. So now if I look at the left-hand side and then I expand it, then I should say, actually, maybe I haven't explained the unitary. So basically, unitary is the linear transformation. The specific thing about unitary is that it is its own inverse. So it's just a linear transformation matrix, but it is its own inverse, and that's very important for quantum mechanics, because in quantum mechanics, unitary is the important property to have the observables. But let's not go into that. So because unitary is a linear transformation, so then if I break it up, this left-hand side, and then I can apply unitary in either of the individual components. And then I actually have this state on the left-hand side, which actually doesn't really look like it will have this state on the right-hand side. Because if I expand the right-hand side, then I have these cross terms between 0 and 1 of system A and B. So what it means is that either the superposition of these qubits of 0 and 1 is not really possible in reality, or maybe it's true, maybe the cloning, the copying information, quantum information is not so easy. So it turns out that actually copying quantum information, just a simple way we do classical information, is not the not the way we can do it. And this thing is actually called no cloning theorem. So this is a very important thing. But here I should mention that although no cloning theorem basically says we cannot copy a quantum information with 100% certainty from one place to another place, but it doesn't say if we reduce the fidelity, say if we say we want to copy the information with 80% fidelity, then whether it can be done or not. And there are a lot of theories which actually says it's actually possible if we don't care about how well we can copy from one place to another place the quantum information. But this is something very important, like very profound, that the quantum information, the qubits, once we talk about superposition, then it becomes very different. Like we cannot simply copy from or send quantum information from one place to another place. So what can be a way to send quantum information from one place to another place? So one way is that when we have quantum information on a object, we can send that object by itself, but that sounds very odd. I mean, say that basically means, like, if we think about classically, that means that if you want to send the information that's in my laptop to someone else's laptop, then actually have to carry the laptop all the way to someone else, not actually send the information through the channel, the communication channel. So the other option is actually what is called teleportation. So in teleportation, what we require is an entangled state, for example, a Bell state. So what it does is that if I explain it through this equation here, it basically says that if you have a Bell state, entangled state, and I want to transfer this qubit C from to say from the object C to somewhere in object A. Object A can be somewhere very far, the distant user. Then using some transformation, I can actually transfer C, the qubit in C to A, qubit in A. In simple terms, what it means is that I have a Bell state between A and B are distant users. They are far apart, and the communication channel is basically the Bell state between them. And then when if I want to send an information from C to A, then I do some measurement, which is called the Bell measurement between B and C, and it teleports the quantum information from C to A. So I'm going to explain all these things in details in the coming slides, what the Bell state means and what does it actually mean doing these Bell measurements. But before going there, I just want to mention two important things. The teleportation teleportation only means that it transfers the quantum state. It doesn't actually means we teleport our whole I mean, it doesn't mean the teleportation we understand from Star Trek or Star Wars or those kind of movies or series. Maybe that's possible if we actually reduce all of our information in our body, everything in our body in just mere information. But even then, there will be questions like, what about our mind or soul? Does it have any, can those be also represented by information? If you can transfer, if you can represent everything in our body as information, then perhaps we can do teleportation from one place to another as a big object. But I mean, at the moment, it just seems unlikely. The another important thing is teleportation doesn't actually put any constraint how far this object would be, and sometimes some people may think that it's instantaneous or it does not obey relativity, but it does. I'm just going to explain why these things actually people talk about when I'm going to explain the Bell state. So let me start with Bell state. And Bell state is an entangled state. So let me first explain what entanglement is. And these explanations I quite like. I think they are very easy to see and easy to understand. And I have taken basically this from this paper by John Norton. So if you want to know more about it, I think John Norton has a lot of this sort of explanation, like little cartoons or things of that sort, which can easily explain the complication of quantum mechanics or the philosophy of quantum mechanics to some extent. So entanglement and EPR paradox are related to each other. Entanglement basically came out of the EPR paradox. So, but let me explain entanglement first. So let's consider a box, a two-sided box, left and right. And we say a particle, say a photon inside this box are basically be either in the left side or the right side, but we don't know which side it would be. And then let's say we have two of these boxes, A and B. And then the photon in box A can be either left or right, and photon in box B can be either left or right. And then we bring them close together, and then they have some interaction, and the interaction will determine where the photon will be in the boxes. So if I represent this interaction with this diagram, say in the say in this axis is the A space, the space of A box, and in this axis the space of B box, then say the interaction it happen in such a way that both of the photons, if we manage to see, then we will find both of the photons either in the left side or both of the photons in both of the boxes in the right side. So the interaction essentially entangles the particle. And from this figure, you can kind of see entanglement perhaps means some sort of correlation, like the relation between two parties or two objects or two quantum states. So now the question is, what happens after, okay, the boxes, we put them together and there has been some interaction and entanglement, but then what's going to happen with this? So let's say we put the boxes really, really far apart, say one in Earth and another one we send it to, say, Andromeda or a different galaxy. And then if we measure the photon in box A, say we open the box and we try to see where the photon is, and say we find the photon is on the left side of box A, then what will happen is that if we see where the photon is in box B, we will always find it in the left side, even though the box B is really, really far apart, say in a different galaxy. So what happens is that we measure in box A, and there is a collapse of the wave function in box B on the left side. So what it means is that in terms of this space diagram, is that we are left with only one of the lobes, like only one of the outcomes. So it may appear to be instantaneous, but it's actually not. I mean, so the collapse of the wave function is instantaneous. So we measure it in box A, and then it automatically makes the photons in box B to take a certain state. But what happens is that when people measure in box A and box B, even if it's in far distant galaxies, the two objects A and B, there is still no communication between them. So they actually don't know what the others have found. So if people have measured in box A and found them to be on the left side, and then they measured in box B and they found it in the left side, but even then they have not communicated with each other that where they have found these things. And that's why this collapse of wave function actually does not carry the information, because information basically means that what we know or we can know. Okay, let me now go to the Bell state. Okay, so before going to the Bell state, so let me explain a little bit of the history. So the entanglement basically was coined by Erwin Schrödinger, and it actually came out of the EPR paradox, which is basically put forward by Einstein. So both of them actually didn't like quantum mechanics. So the EPR paradox actually came out of this paper by Einstein, which essentially says that quantum mechanics is wrong because quantum mechanics suggests that if you have a source, say, which is generating a pair of photons, photon 1 and photon 2, it's very similar to the photons in the boxes that I have described before, and they have this entanglement or correlation between them, then when even if they go really far from each other, measuring one will affect the measurement of the other or the state of the other. And since Einstein was the proponent of the special relativity and the speed of light being finite and the same in all medium, then he basically said it's not possible, quantum mechanics is wrong. But what happens is people actually has this system, these quantum systems, and they measured it, and then they found that it actually happens the way it has been asked that it cannot happen. And then basically people found that actually is the entanglement does exist, and the EPR paradox essentially points out this weird but interesting feature of this quantum mechanics. Although I have said entanglement is correlation, I should point out that entanglement is a very special kind of quantum correlation. So here in their paper, they have tried to explain correlation in terms of classical mechanics or classical physics. And then they found out that with classical physics, it cannot be explained. And that's why they decided, since it cannot be explained by classical physics, that's why entanglement is wrong. It doesn't exist. Quantum mechanics is wrong. But then people found out actually entanglement is correlation, but it's very special kind of correlation, which can only be explained by quantum mechanics. So that's one of the distinctions that I should make. So these states, actually, they have no classical analogs. So what a Bell state? So in the example of little boxes, we have these boxes where both of the photons are on either the left side or on the right side. Say if we now denote left side being 0, the state of being left side is 0, and the state of being the right side is actually 1, then we can represent this quantum state of a photon in box, say, as a qubit, with alpha and beta being the relative amplitude of photons to be found either in left side or the right side. So then psi basically represent a superposition of 0 and 1, the same way we have the superposition of 0 and 1 in the boxes, little boxes before. A Bell state is then representing this diagram here on the right side, the joint state of the quantum objects. So the joint quantum state of object A and B, or the photonic state A and B. And it represents in this way. So essentially it means that if we measure 0 in A, then we find 0 in B. Or if we measure 1 in A, we find 1 in B. So this is one of the maximally entangled Bell states. So there are 4 of them. Let me recap a little bit before I show the implementation. So these are basically the fundamentals that is needed to understand the implementation of teleportation using photonic circuits. I first explained photonics. I mean, not explain, I basically pointed out the components that I will use in photonics, and then what a qubit is, and then the no cloning theorem, or how is not so easy to actually copy information in quantum information theory. And then teleportation, one of the ways to copy information. And then the resource needed for teleportation, which is entanglement. And then the Bell state, which you use to teleport something. So before I go further, if anyone has any questions, then I can just go back to the slide and explain it, because that would be very important to understand the next steps. Does anyone have any question?
Yeah, Bell states, I couldn't get your Bell, understand Bell state.
Okay. Okay, let me go back. Did you understand the entanglement?
Yeah.
Okay, right. All right. So, let me just talk about entanglement briefly. So say here, when we put these two boxes together and they have some sort of interaction, and that interaction entangle them, and that can happen many ways depending on how we interact them. And say here, both of the photons interact in such a way that they will be both on the left or the right side. So Bell state essentially represents this interaction, so mathematically. So say physically, we say the photons interact, and we can find them either in the left side or the right side of the boxes. But in mathematically, how we will describe it? So the way we describe it is the Bell state, and if we look at it, it essentially looks like a superposition. So, for example, qubit is a superposition of a single quantum object being in two different states. So when we have a single box, we say the photon is either on the left side, which is represented by 0, or on the right side, represented by 1. But the photon is never in both of left and right side at the same time. So that's the idea of representing a single quantum state through a qubit, for example. So it doesn't actually have to be qubit. There could be more than one state, more than two states. So there can be 3 or 4, and then it's qtrit or qdit, all those kind of things. But say we just talk about qubit. So superposition is the same. Using superposition, we can explain it the same way for the single quantum state for B as well. But now when we have a joint object, so when we have more than one, say we have two objects and they are related to each other in some way, and they both are superposition of some sort of superposition state, then how we express them mathematically. So say we take the individual joint state, and then we see the superposition of them. So that is one way of representing them. For example, we say that when the interaction and the entanglement happen, then the both photons we will find either on the left side or the right side. So when we find both of them on the left side, then we represent then the state of that is both 0 for A and B, right?
Yeah.
Okay. And then when we say we will find both of them on the right side, then the state is represented by 1 for both of them.
Yeah.
But then we say, then we apply the superposition. Then we say we will find both of the photons either on the left side or on the right side. So that's how this plus sign comes into the view, because we have the superposition of these two different states, joint states.
So it's going to be either or.
Yes.
Okay.
Yes. So that's the main point of superposition. So the Bell state basically is a superposition state, just like a qubit,
Okay, fine.
but it's a superposition state between more than one object, or among more than one object. So it's a superposition state for, in this case, between A and B.
Right.
And okay, so the requirement of this being Bell state is they are maximally entangled. So I mean, we can imagine there could be other possibilities here, like they are both in left and right, or they are both either in left or right, and that could be some other state that could possibly happen. But that will not be a Bell state. That will be still an entangled state, and that can be represented by a joint state. But that will not be Bell state. Only this state is maximally entangled. And actually, I haven't explained why it's called maximally entangled, and I think I cannot explain it because that will require a lot of theory and mathematics. But in simple terms, the entanglement is measured with entropy. So in information theory, how much information we gain or send somewhere is measured through the entropy, the information entropy. And the relation between how much two states are entangled is also related to the entropy.
Are there any,
So,
will there be any constraints or conditions for the states to be entangled?
for example?
Say, for example, we understood that if the photon is there in the left side, even if the other box is far away, or the other, when you do the measure, there is. So if it has to be visualized or felt in the real life, are there any constraints like, or we take it and then we proceed with the quantum Bell states and proceed with it?
It just proceed with that. So, I mean, there is no real constraint. So, I mean, these objects can be anywhere, or they can be anything. When we talk about photons specifically, okay, so I should mention one thing. When we talk about photons specifically, usually photons do not interact with the rest of the world that much. So, I mean, the easiest way to understand is that we can see lights from distant stars, from distant galaxy, to Earth, and they have traveled billions of light years. So photons do not travel, I mean, hardly photons travel without any disturbance from others. But if we talk about other quantum technology, quantum objects, which are say electrons or other things, then they do interact with the environment quite a lot. And for them, there could be some specific constraint, like how far we can take them before the entanglement disappears, because the decoherence, like the interaction of the electrons of the quantum system with the rest of the environment, which then mixes up the state, and the entanglement, the correlation between them disappears.
Even a non-coherent source, you can talk about entanglement?
No, this is exactly the point actually, because when we talk about non-coherent source, then because non-coherent source usually reacts, or actually it interacts with the environment severely.
Okay.
So that's how it becomes non-coherent. So when quantum systems interacts with the environment severely, say for example, say spin systems or so, then I think the entanglement can exist perhaps in milliseconds time scale, or I think microsecond is probably the maximum they can stay.
Yeah, right. Thank you.
Right, thank you. So thanks for the question. Anyone else want to ask anything? Let me go back here. No other question? Okay. Okay, so let me explain how a teleportation is implemented in a photonic circuit. So what I have talked about until now, they all just seems like interesting philosophical questions or theory, and they have been for a long time. I think maybe in 90s or maybe early 2000, people actually started to test them in real life and started to making technology out of these interesting philosophical questions. And one thing I should mention before going further into my slides is that a lot of these things that we do, sometimes we just turn off our brain and just do it, because a lot of these things, this concept entanglement, sometimes when we make things complex and bigger, it becomes quite hard to actually follow. So we first do it and then we try to figure out what's happening. So don't worry if it seems to be too complicated or like this circuit. So I am just putting this circuit up front, not to scare you, but just to give the overview, like the big picture, where I'm going with my next few slides. Okay, so this is our whole quantum photonic chip for teleportation. So let me start from the very left-hand side. So we have a pulse which comes into the chip, and you can see these things here, which are actually the input that I mentioned at the beginning. These are called grating couplers. There are very specific designs of grating couplers in this very specific case, but they couple the light to the chip and the light goes through. And these are the Mach-Zehnder interferometers that I have explained at the beginning, the symmetric ones. The path lengths are the same on both arms. And they split the light in some specific way. And here they split the light in equal amount in all the output ports. And there are 4 output from this Mach-Zehnder array. And then they go through this structure, which is called a ring resonator, which I have not explained in the past, because I'm going to explain in the next slide. And the ring resonator looks like this. It's basically a ring. That's why it's called ring. And the resonator part is because it's almost like a loop. And then a light goes inside and then just goes around like a cavity. And that's how it's called a resonator. So what happens in the resonator is that they generate a pair of photons, and these asymmetric Mach-Zehnders then separate this pair of photons, which are basically of 2 different colors, say red and blue. And then they go through this part, which is called the preparation part, or to make them qubit. And then they go through this operation part, which is like a processor for electronics, like analogy to a processor in electronics. And then at the end, we have this measurement part. And then we can have 2 different chips. And then we can transform the photonic state, the quantum photonic state, from one chip to another chip for teleportation. Okay, let me actually now break down this whole picture, this whole overview of the chip. So just before going to the next slides, so the main thing here in these diagrams or figure is that we have input and then we have output, and then in the middle we do some manipulation. Okay, so let's start with how we get the single photons. So I talked about single photons and the photonic state, but in reality, it's actually not so easy to get a single photon. At the end of my talk, I'll just briefly mention the problems with getting a good single photon. For the moment, to understand the next slide, just let's consider we have this structure, this ring resonator. When we shine a laser light through it and the light goes around, it generates a pair of photons, this red and blue, and they are always generated as a pair. Since they are always a pair of photons, then if we detect one of them, say we detect the red photon, then we herald the presence of the blue photon. And that's how we can always say there is a single blue photon here, and that's how it acts as a single photon source. So for this one to access a single photon source, we always have to detect one of the pairs, the red one, say for example, or the blue one, but one of them always. Okay, so having that in mind, let's consider how we generate a qubit or prepare a qubit in a photonic circuit. So this structure generates a pair of photons, and then we separate this pair of photons with this asymmetric Mach Zehnder, which acts as a filter and filter one photon to the top arm and filter out another photon to the bottom arm. And say we detect the red photon, and then we know there is a blue photon in the circuit. So I should actually mention before this, but probably you already have guessed, this these thick black lines are essentially the waveguide that's carrying the photons around the circuit. And these ones are the beam splitter or directional couplers. And this is one directional coupler and the directional coupler, and these are the two arms of the Mach Zehnder. Okay, right. So if you have any question, you can always ask me as well. If I haven't explained it very well, you can ask me. So now say we detect the red photon and we have this blue photon on this top waveguide. And then what we have here, so what we have here is the preparation of the qubit. So here it goes to this symmetric Mach Zehnder, and we call it unitary U. So I mentioned before, Mach Zehnder is a very versatile component. It can do a lot of things. So because it's almost like a variable switch, then we represent it in this transfer matrix of this Mach Zehnder. And it's actually unitary, this transfer matrix. And then if we have a phase shifter after that, like which introduce a different phase only in the top arm to the phase, and then we calculate the final photonic state out of this Mach Zehnder and this phase shifter. Then we come to this equation, say, and this equation we can see it does appear to be it does appear to look like a qubit state of 0 and 1, superposition between 0 and 1. So by tuning the phase phi of the Mach Zehnder and the phase theta of this phase shifter, we can actually get an arbitrary qubit. So this is how we prepare a qubit for a photonic in our photonic circuit. So what it means is that we can choose phi, say phi equal to 0, then we get a photonic bit, say a photonic qubit, which is prepared in one state. So what it means is that the photon will always be in the bottom waveguide, say here. And if phi is say 90 degree, then we have the 0 state, which means the photon will be always in the top waveguide. And then when we have say phi equal to say 45 degree, then what happens is that it would be equal superposition between 0 and 1. So photon would be 50% of the time the top waveguide and 50% of the time the bottom waveguide. So, and here again, I should mention that photon cannot be in both of the waveguide at the same time. So we cannot find photon both in the top and the bottom waveguide at the same time. It would be in either of them. Okay, so this is how we prepare a qubit in a photonic circuit. And then let's talk about the Bell state. So how do we prepare a Bell state in a photonic circuit? So it may look quite mundane or maybe complicated, but let me see if I can break it down for you. Okay, Ben. So say there is a postulate here. The postulate here is that we have this structure, the ring resonator, which is generating a pair of photons. So the postulate here is that either one of the structure will generate a pair of photons, or either one of the structure will fire at a time. So not both of them will generate a pair of photon each at a time. So say, for example, only resonator 1 is generating a pair of photons. And then this asymmetric Mach Zehnder is separating the pair of photons from blue and red. And say the red one is, can I change the ink? Yes, red, okay. So the red one is then going up here. And say these two waveguides are qubit 1. And so if in the top waveguide of this qubit 1, so it's 0, it's state 0. And then the blue photon is going down. So the blue photon is going down here. This is the crosser, waveguide crosser. So it crosses, it's like electronic crosser, like two electronic pair crossing each other. So this blue photon is going down. It comes here. And then we make the unitary as identity and theta equal to 0. So unitary identity means that as a switch, if we incident something from the left side on the top, it will end up on the right side on the top. So then the photon goes through all the way here. And this is the bottom qubit, qubit 2. And it's in the top waveguide of the bottom qubit. So that is also 0. So it means that when source 1 fires only, then we have 0 in the bottom top qubit and 0 in the bottom qubit. So we have this 0 and 0 state. So now say only the second resonator fires, then what happens is that say the blue photon is going down and going all the way here. So we have 1, so qubit 2 is 1 in the bottom waveguide. And for the and then the red photon is then going up and is going to the bottom waveguide of the qubit 1. So that is also 1. So then we have 1 and 1. So if we don't know which one is firing, 1 and 2, so that is another important postulate here, then we cannot know whether resonator 1 is firing or 2 is firing. But either one of them is firing at a time. Then we end up with a superposition state that either the photons are both in the bottom waveguides of the qubits or the top waveguides of the qubits, and we have 0 and 1. And that actually looks like a Bell state. So I mentioned before that there are 4 maximally Bell states, maximally entangled Bell states, and they're actually called phi plus minus and psi plus and minus. And what it actually says is that for phi plus, we have 0, 0, plus 1, 1, or 0, 0, minus 1, 1. And for psi plus, we have 0, 0, 1, plus 1, 0. And psi minus, we have 0, 1, minus 1, 0. Okay. Right. Okay. So so this is how we generate the Bell state. So we now have the Bell state and the qubits to do the teleportation on a photonic chip. Yes. Is there any question? No. Okay.
Dr. Imad, I had one.
Yeah, please.
Yeah, so you explained about that generation of pair of photons in the microring resonator.
Yes.
So what is the exact physical mechanism behind that? Is it because of the high pump energy which you are pumping it into the ring cavity, and then because of the nonlinear effects, or what is the physics happening behind that?
Exactly that. How much time do I have?
You can take your time. There's no limit.
Okay, all right. Okay, I will.
You have your content to be delivered. Only interested participants are there, so you can feel free.
Okay, all right. Okay, so I will probably not take more than 15 minutes. Okay,
Fine.
so Yeah. Okay, so I'm going to explain that part, the part you have just mentioned, the nonlinear interaction and generating photon pairs in a moment. You are right, that is how it's happening, actually. Okay, right. Shall I go forward?
Yeah. So I just wanted to clarify, is it because of the nonlinear effects or something else is happening there?
No, that's the effect. Yeah.
Okay.
Okay. All
When
right.
you're one more, when you're writing this ciphless, you have 0, 1.
Yes.
Is that the entangled states then?
Yes.
Are entangled?
Yes. So anything that's written this way is called entangled state. So one way of seeing if it entangled state or not mathematically is to see if we can factor it out. So if we can factor 0, say object 1 or object 2, you can factor it out so that we have a multiplication of 0 and 1. For example, if you only take this part, let me take this. So if we only consider this part of this superposition state, only this part, and we forget about the other one, then it's actually not an entangled state. So it's what it is called a separated state, because we have 0 state from 1 multiplied with 0 state of 2. Just simple multiplication or factored out. And then the same with this one. But then there is a plus here, and we cannot factor out one state of 1 with state of 2. So that's why it's entangled. So if we have 0, 1 and 1, 0, then it's still entangled because we cannot factor it out. So there is all these 4 possibilities of being 0 and 1 here, and then plus and minus here. So that's why there are 4 maximum entangled belt state.
Okay.
Okay. Okay. So shall I go forward?
And then I also want, one more thing.
Please.
How do we make sure that only one ring fires at a time?
Yeah, this is a very good question. So this is a limitation of this scheme. So there are different schemes of generating belt state. And the limitation of these schemes is that we have to make sure that the power of the laser going through the rings are very low, that at a time only one of the ring can fire.
Okay.
So that's the big limitation. So sometimes that doesn't happen. So sometimes both of the rings are generating photons, and then it's the invalid qubit, and it doesn't work.
Okay. And the diagram which you showed earlier, the big diagram, which I think I saw in the physics.org newsletter also. So is this experimentally evaluated or?
Yes, this is experimental.
Wow.
Yes.
So you have the fabrication facility in your university?
No, so this has been, okay, so this is actually a separate question. So fabrication now these days happens in very different ways. So the thing is called multi-project wafers. Okay. So multi-project wafer basically means there is a fabrication company somewhere in the world. There are quite a lot in Singapore, Belgium. And what they do is they have this big wafer, and people can actually pay, say, about 2 to say 4,000 or 5,000 pounds per chip. And they have this big wafer, and they collect everyone's design. And then they fabricate the whole thing at a time. And then they ship us back the part of the chip that we designed. So that is very important, because fabrication facilities are actually, good fabrication facilities are actually very difficult to come by. And so that is one way. But this one specifically has been fabricated in DTU, the Denmark Technical University.
So this entire thing is on one single chip, or you are integrating different parts like Mach Zehnder, ring resonator, then couplers?
No, the main important thing about integrated photonics is that the whole thing is monolithically integrated, because that's what ensures the stability. So for example, if anyone has done experiment with an off-chip Mach Zehnder mixed from bulk optics, say beam splitters and phase shifters, then they know that it's very difficult to keep the Mach Zehnder stable in the exact same position for more than 1-2 days.
Yes.
For integrated optics, everything is integrated in the same chip, and that's why the stability is ensured.
Okay.
So the Mach Zehnder stays in the same position forever.
Okay. And I think the power loss also must be a bit high in this case, because there are so many waveguides and other components integrated.
What do you mean?
I think the loss incurred in the signal must be very high in this case, because the waveguides and there are many components integrated together.
Right. No, actually, okay, sorry, yeah. I mean, it depends how big the circuit is. So the linear loss in silicon photonics at the moment is about 3 dB per centimeter, or say 2 dB per centimeter.
Yeah.
It can be 1 dB per centimeter.
Yeah.
But you can see the size of the chip is millimeter. It's much lower. So the linear loss is almost not felt at all.
Okay. Okay, thank you.
Yeah, welcome. Anything else? Okay, then let me go forward. So we have the photon pairs here. We prepare them in a qubit that we want to teleport, and then we have the Bell state here. So now in the next part here, let me explain how we teleport this qubit with the Bell state. Okay, so say we have this Bell state generated here from this qubit. It goes to this preparation stage, and then we have the qubit here. And then we have the Bell state generated from these resonators here, and we have the Bell state here. This is the Bell state. And then here we do something, but before coming here, let me just express how the system looks like at this point. Like at this point, how the system look like. So we have this psi3 qubit, and we have this 5+ Bell state. And then I express it explicitly with the equations. And then in the next step, what I do is I just rearrange them. So I have not done anything physically. I'm just rearranging them. So the Bell state was between 1 and 2, and the qubit was in 3. And then I'm going to rearrange it, and I'm going to write the Bell state in terms of 2 and 3. So it's just essentially rewriting. I'm not doing anything else here. So it's just rewriting a line of equation to a different line. So I express the Bell state now between 2 and 3. And when I express the Bell state between 2 and 3, then I can see that the rest of the state of 1 looked like actually psi. So this was psi in 3 in here. But when I write it down as a Bell state 5+ between 2 and 3, then it looks like psi in 1. Okay. So this looks very trivial, but this is very significant. So it's just rewriting, okay, at this point. So when we rewrite it in this way, we actually get 4 possibilities. So Bell state actually for this maximally entangled Bell state, they form a basis. So the basis of this 2 by 2 Hilbert space. So because it forms a basis, then when we express it in other forms, say from 1 to 2 to 2 to 3, so we get these 4 possibilities of these 4 different Bell state. So if we express it in terms of 5+ for between 2 and 3, then it becomes psi 1. But if it is become phi-, then it not exactly psi 1. Oh, there's a bracket missing here. It's not psi 1, but it's like psi 1, but with a minus sign here. And then for psi plus 2, 3, the 0 and 1 exchanges, like the alpha and beta is different here. And then for psi minus, sorry, there is another bracket missing. So for psi minus, then there is this form it. But these can be, once we know which basis it is, so with this psi minus or psi plus, then we can actually transform this qubit and then make it psi 1. So now I just rewritten it in terms of 5+, phi-, and psi minus between 2 and 3. And then what happens is that now I'm going to measure it. Say if I now measure the 5+ in terms of Bell state between 2 and 3, say 5+, then I will collapse this part. And because this is connected to this psi 1, then if I measure the Bell state, if I measure between 2 and 3 as a 5+ Bell state, which is called the Bell measurement between 2 and 3, then I'm going to teleport psi 3 to psi 1. So that's the most important thing. So to teleport something between say 3 and 1, I actually need a communication channel between 1 and 2 as a Bell state. So that's the resource I need to teleport something from 3 to 1. So that's the main thing here. So now the question is, how do I measure 5 plus that? What is the Bell measurement, or how do I measure 5 plus 2, 3 between 2 and 3? So I'm going to explain it in the next slide. So bear with me. It may look a bit complicated, but I can explain it. So this measurement is called Bell measurement, operator Bell. So say I have, say, for example, I have 2 and 3. So I have 2 and 3 here, right? Qubit 2 and 3 that I'm going to do Bell measurement on. So let me first explain how 2 and 3 generates a Bell state. Okay, let me choose pen again. Okay, so say I prepare state 2 and 3 in qubit 1 and 0. So qubit 2 in 1 and qubit 3 in 0. So qubit 2 in 1 basically means there is a photon here, and then at the bottom waveguide, and there is a photon of qubit 3 in the top waveguide. And then the operation here is exchange. So the photons goes from here to here. And then there is interference. So in interference, there are single photons in the interference. Photons are only one of the arms. So the photons can either transmit or reflect. And the same thing here, the photons can either transmit or reflect. Okay. So if both of the photons transmits, okay, so then there is another exchange here, and the photons actually comes up here. Okay. So then we actually have several possibilities, like both of the photons transmitting. Then we have photons here and here. So which would be an invalid qubit. This is the invalid qubit because there are photons in both of the arms, or both of the waveguides in the qubit. And then there are, if the photons are actually here and here, this is also an invalid qubit. And then if there is a photon in here, then the other possibility is the other photon would be, sorry, let me actually change the color. So if there is a photon in here, then the other photon will be here. And when there is a photon in this waveguide, then the other photon will be here. So it's like 0, 1, and 1, 0. 0, 1, and plus 1, 0. And that is the psi minus state. Okay. So there are a few things here I need to point out. You can see there are garbage generated in this scheme. So by garbage, I mean like invalid qubits. So the fidelity or the success rate of this scheme is not 100%. I think the success rate is actually 50%. That's the way we get psi minus. And you can see this is a linear circuit. So it can go forward and it can go backward, and nothing needs to be changed. So it means that if we can generate Bell state from left to right, we can measure Bell state from right to left. So the same configuration circuit, and if we input a Bell state on the left side, and we monitor the generated photon pairs on the right side, then we can actually measure the Bell state. Okay, the psi minus Bell state in this way. So this is how we do the Bell measurement. So we configure the circuit in this way, and then we can measure the psi minus, and when we get the psi minus, we measure the psi minus between 2 and 3, and then that teleports the qubit from 3 to 1. There is another operator which is called fusion operator. So this fusion operator can generate the phi plus phi minus Bell state, and then using this fusion operator, then we can actually do the measurement of phi plus phi minus Bell state between 2 and 3, and that teleports the state from 3 to 1. So I'm not going to explain the fusion operator in detail. It is very similar to this. You just need to propagate the photons, and then you can see what happens here. This is the transfer matrix in short. So if you don't want to go through in detail, all you need to do, you need to multiply the transfer matrix on the left side of this the 2-qubit system, and on the right side, after the multiplication, you will get this state. So so this is a bit of mathematics, but in terms of bulk optics, this situation, this Bell measurement, it looks like a polarization qubit, vertical and horizontal, incident on a beam splitter, And for this operation, fusion operation, it looks like a polarization qubit incident on a polarization beam splitter. And it gives exactly the same transfer matrix and exactly the same result. Okay, all right. This could be a little bit different because this slide, I mean, if you want to ask, you can ask questions on it. Otherwise, I'll go to the next slide. Okay. So one last thing in this circuit I want to mention is that these methods can be used also for entanglement swapping. So what it means is that if we have entangled state between 1 and 2 and 3 and 4, and then it propagates through the circuit, and we do a Bell measurement between 2 and 3, then it makes 1 and 4 entangled. So this is called entanglement swapping because 1 and 4 before had no connection between them. They are separated object. So 1 and 2 was one system and 3 and 4 one system, and they had no connection between them before. And once we measure 2 and 3, then it swaps, it actually distributes the entanglement from 1 and 2 and 3 and 4 to 1 and 4. This 1 and 4 which never had any interaction before. So here actually I just pointed out the experimental data which shows the fidelity of this operation. So sorry, let me go back to the previous slide again. So also like this data essentially is saying how good the experiment results were. So the fidelity of this operation, when we measured it at the end, after doing all these things, we find it to be 85% fidelity. So when we generate the psi minus, it was good enough, about 85%. It was not 100% psi minus, it was almost there. So that's the experimental imperfections. And the same way, we have 83% of Y plus. Preparing a qubit is actually very high fidelity. So when we prepare the qubits, we prepared it with almost 99% fidelity, like 1 in qubit 2 and 0 in qubit 2. They were actually 1 and 0 in qubit 2 and 3. So the same way, the fidelity on this operation was about 70%, which is not very high, but is good enough to show its quantum. Okay, so just overview what I have just explained. So we have this pulse coming in here to generate single photons, and then we did this manipulation here. What did the teleportation and say entanglement swapping, and then the measurement here is actually verified that they are quantum states. Okay, so now I just briefly going to mention this bit, which is the single photon generation. So the single photon generation is actually one of the most difficult part, like the fidelity I had mentioned before, which are not 100%. And quite a lot of time they are not 100% mainly because our single photon sources are not perfect. So I'm going in a completely different direction now from previous slides. So here I'm just going to explain just what single photon source should be and what we have actually. So the single photon source, ideal single photon source is something where we press a button and we have a single photon stream, which are always regular in regular interval. They're always in single optical mode, and they are always one single photon, and they are always indistinguishable, one photons to another. And if we have two different sources of single photons, they would be completely indistinguishable. But in real life, they are not that. In real life, when you press a button, sometimes there is no photon, and sometimes there are two photons close together. Sometimes there are more than one photons, and sometimes photons are very different from each other. So they are in different optical modes. And so in reality, the way we measure is like how many photons are there is like the brightness per second. And then the purity is how many optical modes are there. If there is always one single optical mode, then the purity is 100%, but usually it's not. And then there are more than one photons, these multi-photon terms. That makes the situation difficult. For example, in previous slide, I explained at one point, if there are two photons in a qubit, then it's not a valid qubit anymore. So I said before that we, I mean, just for the sake of the argument, just consider we generate a pair of photons. So the way the photons are being generated is called spontaneous Fourier mixing. So the reason we have these multiple photon pair terms, it can be understood this way. Let's say we have two single photons from the laser. Okay, now let me start this way. say we have this silicon material, which is this nonlinearity called chi3. And then we have a strong laser pulse, which is alpha. And then we instantaneous this alpha into the silicon. Most of the time, alpha just goes through the silicon and there is no change, nothing happens. But once in a while, what happens is that two single photons of these pumps, say these green photons, goes to the silicon, interacts with them, and then it disappears into the vacuum. So this is the important part here. The silicon nonlinear material managed to make interaction with the vacuum through this laser pulse. So when these two photons disappears into the vacuum, so a pair of photons reappears from the vacuum to the silicon, but in different wavelengths. And these are called historically Seaton and Idler. They are always in a pair, and they're usually, depending on the configuration, they're in different wavelengths. So then detecting one of them makes the presence of the other, which is called heralding. So the reason we can have more than one pair of photons is that there is nothing stopping the pump rather than absorbing two photons into the vacuum. It can actually gives 4 photons into the vacuum. And rather than one pair of signal idler, we can have 2 pairs of signal idler, and then it will have more than one single photon. And that's one limitation of the single photon source. And the other limitation actually comes from the whole process. So this whole process is conserved in energy and momentum. So this whole process, if it's conserved in energy and momentum, and if we express this whole process with this equation, which is usually called joint spectral density. So this joint spectral density actually shows how many optical modes are there. So the way we actually detect how many optical modes are there, actually, once we have this equation, and then we express it in terms of energy, in terms of a series, a decomposition. Say it's called Schmidt decomposition, which is very similar to a Fourier series. Say once we have this f, if we decompose using Schmidt decomposition with these orthogonal functions, and the lambdas here, the factors here is basically saying how many, what's the weightage of the optical modes here. So in ideal case, we want lambda 1 to be 1 and everything else to be 0, lambda 2, lambda 3 equal to 0. And then there is only one single optical mode. But in reality, lambda 1 is probably 90% and lambda 2 is something says 7, 8, and the rest continues. And that actually changes the whole, that actually makes the operation of this whole circuit or these schemes very imperfect, because there are now more than one photons in the circuit, and there are more than one optical mode which can have more than one photons. So now the whole thing becomes a lot more complicated, just rather than just being one single photon in each case. So I think I should finish up. Right. Okay. So so there are different ways of actually making things better, like increasing the number of the optical the purity, which is making this spectral mode. So we can have a resonator in different configurations, or we can manipulate with the pump pulse, and then we can change the purity of the single photon state. If you want to ask me about it, please ask me. But let me go to the conclusion. So, okay. So in conclusion, I think what I have talked about at the beginning is the integrated photonic chip actually offers a scalable optical platform, because we believe that if electronic industry can have 1 billion transistor, then a photonic industry can have 1 million qubits based on the same platform. And silicon photonics, the same reason silicon photonics we think is capable of implementing complex quantum algorithms. And using this current technology and silicon photonics, we sufficiently have shown chip-to-chip quantum teleportation and some other photonic communications, the entanglement swapping. The fourth part I actually haven't explained very well. So the fourth part basically saying is in this cavity engineering, in the single photon source, the purity of the single photons can be increased arbitrarily. So we can have single optical mode almost to the point we have 99% spectral purity. But I should mention that, so I have only mentioned that the challenge of single photon source to be perfect, but there are other challenges, like loss is actually one thing. Although before I mentioned that for this particular chip is only millimeter size, so the linear loss is not a big issue. But once we talk about 1,000,000 qubits, the size of the chip will become really large, and then the loss will actually play a dominant role. Also, the detection, I haven't talked about the detection and the speed of the Mach-Zehnders, how fast they can switch, all these things. So there are actually a lot of challenges that needs to be solved to go to this 1,000,000 qubit milestone. But I mean, we are hopeful that maybe the photon technology will manage to go there at some point. Okay, thanks for listening. I'm sorry, it's been quite a long talk, and thanks for bearing with me.
It was really interesting, a new topic for us. We just read here and there through literature, but first time listening to a speaker, expert in it. So it was really nice. I was about to ask single photon detection,
Yes,
how you were measuring. So maybe just now you said it's became a challenge.
Yes. Let me explain it then. So the single photon detection that we have used in this chip is telecom wavelength superconducting single photon detectors, which has become really good now in the last few years. So the ones we have used is more than 90% efficient. So if there is a photon with 90% efficiency, we can detect it. Okay. But there's first of all, there's superconducting detection, which means we need a lot of infrastructure. It's very expensive. So so we need a lot of government funding to buy something like that. And superconducting means it's cryogenic. So it's like sub-millikelvin temperature. So it's like 0.73 Kelvin, something of that sort. So it's very difficult to actually keep somewhere. We need a cryogenic thing going on, like compressor, which makes it superconducting all the time. So we cannot actually. So I'm saying that this is a problem. First of all, because if we talk about only now, I've talked about only a 4 qubit system, and for 4 qubit system we need such a big thing like cryogenics, a single photon detector. And if I talk about 1,000,000 qubit, then it cannot be scaled up, because then we need like a very big, maybe a city which is full of cryogenics with all these single photon detectors. So that needs to be really compressed and make small and probably room temperature, not millikelvin temperature.
Are these? I am not very sure. Are these single photon research benefit or research interest, or really in practical you foresee to come into picture? Because it's real. Yes. Compared to what is existing now. Maybe out of academic interest or research interest, it's been taken up, or really we foresee that it can come in practice?
Yes, it's a very fantastic question. So I think when I applied for the PhD for this in this area, like I thought it would be more like an academic interest, like there wouldn't be that much interest to make it commercially viable or commercially useful. But what happens in the last 5-6 years, the government started spending a lot of money. So it's all over the world. It's not the Europe only, it's US as well. And I think specifically China these days are spending a lot of money on this area. And the most important area in this quantum technology that all the governments are interested in, probably you can guess, that's secure communication.
Secure, yeah.
Yes, secure communication. So especially for the Chinese government, they now have a satellite, we call Miches satellite. So with the satellite, they have managed to connect 2 cities in China. I think it's almost 1,200 kilometers apart, and they have secure communication, quantum communication between these 2 cities. And there are a lot of other projects in UK, rest of the Europe, and US to make satellite communication, like satellite quantum communication. So I'd say that's the most real application of quantum technology at the moment.
Yeah. And so towards security only we started learning about single quantum, entanglement, etc. But for we taking up the research, I was very skeptical, but it's really interesting to listen to. I was really happy and privileged to listen to you.
Thank you very much.
Thank you very much. And for a patient explaining, like we read a paper, we don't get it. You are so patient enough to explain to us and really got a lot from today's lecture.
Thank you. No problem at all. I mean, I'm happy to explain. I mean, I think that's the main job of a speaker, to explain. I mean, if I don't explain well, then people can just read the paper.
At the end of the day, not all talk, we do get such a knowledge from the speaker.
Yeah.
So really we could get, because it is all something which we didn't know, to be very frank. We have not attempted these. We learned articles, entanglement, single photon detectors, new thing, new has come up. But since we are not interested, we didn't have a into to read in and out of the paper. But I think in future, definitely we can go through papers from the fundamentals which you have got from it. Thanks a lot.
Thank you. Thank you very much. I mean, I'm glad that you guys all enjoyed it and asked me good questions.
Thank you. Thanks for your talk. And Nitina, any questions from the audience?
Dr. Imad, if you don't have any scheduled engagements, can we have for 5-10 minutes, you think?
Yes, of course. Yes,
yeah, because we actually planned for an hour, but I think it's almost 2 hours.
Yeah, sorry, I took a long time.
No, that's really appreciable. And as Shanti ma'am said that not all speakers even show their latest work. My own were all 2020 published papers, so that's really appreciable of you. So
thank you.
I just had one thing, the wavelength range of operation of the first circuit which you showed, teleportation of that chip. So is there any limitation on the wavelength range of operation, or
yes, it's
will
telecom.
that theory be valid for any range?
No. So it's in C band of telecom. So the C band in telecom is the most mature silicon photonics technology. So in the C band, so the reason I say it's the most mature silicon photonics technology, because the good detectors that I said, which is 90% efficient, exist only mainly in telecom C band, and then the low loss waveguides that mainly exist in telecom C band. And the infrastructure, say, for example, if I want to use the optical spectrum analyzer, the very good optical spectrum analyzers, they exist in telecom C band. So if I want to move to different wavelengths, for example, say people want to move to longer wavelengths, say mid-IR wavelength for better communication through atmosphere, there are low losses in those wavelengths. But the main challenge is there is hardly any infrastructure there. There is hardly any good single photon detectors. There is almost no optical spectrum analyzers. The technology is not mature. The loss of the waveguides, I mean, it's a lot of more challenge. So I'd say the main limitation that is in telecom wavelength is actually the infrastructure associated with it.
But will this theory be still valid for higher
Yes.
or lower range of wavelengths?
Yes, it will be valid always. Yeah.
Okay. That's all from my side.
Participants, any queries? Any questions? Clarifications? If none, then Medina, you can wind up formally.
Thank you very much, sir. It was a great learning for all of us. It was very informative to listen on topics like photonics, qubits, the Bell states, and of course the different teleportation on photonics chips. Uh, uh, we thank you very much and for your patience in clearing all our doubts. And we thank you, sir. We have posted the feedback form in the chat box. All the participants are requested to please fill that form. And tomorrow we have Dr. Vivek Kachatia, assistant professor at VJTI Mumbai. He will be taking a hands-on workshop on Optilux, an open source optical system simulator. All the needed tools and the requirements for tomorrow's session will be circulated through mail ID. We invite all the participants to join us tomorrow also. And sir, if possible, if you can join, you also please join us tomorrow at 6:30 p.m. Thank you all.
Thanks again to all the organizers for arranging and inviting me, especially Professor Shanti and Dr. Rohan Kati.
Yeah. Thank you, Dr. Imad. Being a young
Thank
researcher, you have way ahead to go. Wish you all the best in all your endeavors and your research activity. God bless you. We
Thank you
enjoyed
very
it
much.
wholeheartedly. We're sharing your research details. None of them do these days. So I wish you all the best for your future. Thank you.
I wish you all the best as well. Thank you very much. Okay.
Thank you, Dr.
Bye.
Imad, for your kind, patient talk and taking time from your schedule and presenting your latest work to all of us. Thanks again.
No problem at all. My pleasure.
Yeah.
Thanks
Thank you.
again for
Yeah.
inviting. Okay. Bye.
Bye. Bye.